Hey there, everybody. Welcome back. This is Calc 2. We are looking at section 9.2. This is on monotone or monotonic sequence. Helps if I spell it correctly. Monotone or monotonic sequences. Uh, and let's just say why we're doing this. Why are we doing this? If a sequence is monotonic, or monotone, depending on how you like to say it, it's fairly easy to check for convergence or divergence. Okay, so let's just define a monotonic sequence. A sequence A sub n is, we've got a couple ways of looking at this. It's strictly increasing if A sub 1 is less than A sub 2, which is less than A sub 3, which is less than A sub n, dot, dot, dot. For example, 1 is less than 2, is less than 3, less than 4, less than 5. If that's our sequence, that is strictly increasing. And we say it's strictly decreasing if it goes the other way. If A sub 1 is greater than A sub 2, is greater than A sub 3, is greater than A sub n, and you could look at, like, pick any starting number and go downward. You can see that this is always decreasing. And we call these two strictly monotone sequences. Or we say they are strictly monotone. We could have another setup and we dump the word strictly for this because we can have the equal portion here. If A sub 1 is less than or equal to A sub 2, is less than or equal to A sub 3, less than or equal to A sub 4, less than or equal to A sub n. So like if I had 1, 1, 2, 2, 3, 3, 4, 4, some weird sequence like that, that is, we'd like to call this, actually, let me show the decreasing one as well. Of course, it's just doing the same thing, but using the opposite inequality. And we could do a countdown. We could have a bunch in a row. And we say these are monotone eventually. So I gave some ones that were either going and blowing up to infinity or going to negative infinity, and same with these right here, but that's not required. So let's take a look at the way these can turn out. This is called the monotone convergence principle. A monotone sequence will converge. I'm sorry, let me do this in two parts. A monotone sequence will A converge if bounded, which means has a limit, an upper or lower limit depending on what the setup is. Or B diverges to plus or minus infinity if it is unbounded. And the examples I gave previously were diverging monotone sequences. And it's worth noting if the sequence is increasing, i.e. it's going up, for it to converge, it has to have some upper boundary that it can't cross. So if a sequence is increasing, it needs an upper boundary. Or upper bound to converge. And likewise, if it's decreasing, if we want it to converge, it has to have some lower boundary or lower bound, lower limit. Sequence needs a lower bound to converge. So you'll see words like bound, boundary, limit. We tend to use this one in mathematics. That's the most used phrase for what we're talking here. It creates a bound. Boundary makes more sense to me, but I think mathematicians are just lazy in general. And like, that's just got more syllables and takes more shit to write. So, nope. Let's take a look at an example. Let's show that 1/2, 2/3, 3/4, 4/5, etc. is convergent. Well, this is like 0.5, 0.6 repeating, 0.75, 0.8. This is increasing. And the numerator is always one bigger or one smaller than the denominator, so it's always less than 1. So it has a boundary, at least it looks like the upper bound is 1. And since it's increasing and has an upper boundary, this is a convergent sequence. It's important to know, I was able to identify what it is here, but it doesn't tell us what it converges to in general. This principle shows that it converges, but not to what. It converges to. You have to do other stuff to find that out. Now, I did show this was n over n plus 1. Like, I could rewrite it. N over n plus 1 from n equals 1 to infinity. Treat this as a limit. And we multiply top and bottom by 1 over n. We get limit as n goes to infinity. 1 over 1 plus 1 over n. And we can see the limit here does equal 1. So sometimes following this path avoided the principle altogether. So this is like something we only fall back on if we can't figure out what the limit is, we can at least show whether or not it's convergent or divergent. But the idea applies, and it's following this idea right here. Let's look at some more examples, and for not necessarily examples, but how we can deal with this. So there's some tricks to testing for the monotone sequences. Let's see. And we're looking at subsequence a sub n from n equals 1 to infinity. We could do a difference test or a ratio test. And if a sub n plus 1 minus a sub n is greater than or equal to 0, or if a sub n plus 1 over a sub n is greater than or equal to 1, this is an increasing sequence. And we flip these around the other way. If this is less than 0, or if this ratio test is less than 1. It's decreasing. This can be a complicated table to remember, but quick way to think about it is just do the sequences I started with: 1, 2, 3, and 3, 2, 1. 1, 2, 3. Trying to remember which ones they go. If I do a sub 3 minus a sub 2, I have 3 minus 2 is 1, and that's greater than 0. Or if I do the ratio test for these, a sub 3 over a sub 2 is 3 over 2. That's greater than 1. And so these both show increasing. And that's the pattern for finding increasing. And the trick is like just using this to remember what the sign is. These quick little checks can help you remember the sign. And if you're counting down, doing any two in a row, a sub n plus 1 minus a sub n. If I do 2 minus 3, I get -1, which is less than 0. Or if I do the ratio test using 2 and 3 again, this is like n equals 2 and n equals 1. So I use checks here. Here I did n equals 3 and n equals 2. This is less than 1. And they both show less than signs. These are decreasing. That's a way to remember it, a helpful way. You'll get used to remembering this. The ratio one's probably the one that makes most sense. Is the top number bigger or smaller than the bottom number? And sometimes one test works better than the other. So let's take a look at some examples. I'll put that, leave that right there while we're working on this next example. Let's take a look at a sub n equals n over n minus 1. But we're going to do factorial on the bottom. And we'll do that from n equals 1 to infinity. And we will show that this converges to we're just going to show that it converges. Sorry. Show converges. So let's take a look at the difference option one here real quick. And maybe looking at what the sequence looks like will help see us a little bit. So like if I do n equals 1, 2, 3, 4, let's take a look at a few of them. This is 1 over 0 factorial on bottom, which is 1 over 1, which is 1. This is 2 over 1 factorial, which is 2. This is 3 over 2 factorial, which is 3 halves. This is 4 over 3 factorial, which is 4/6. It's starting to go the other way. If I do 5, I've got 5 over 4 factorial, and 4 factorial is 24. So it looks like 4/6. And I know these reduce, but I'm not reducing them to show what they are. The next one in this pattern would be 6 over 5 factorial, which is 120. This is 7 over 720. It looks like it's increasing for a little while. Well, it's increasing there, but then it's starting to, let me change colors, starting to decrease from there. But let's not do the whole monotone principle. Let's use some of the rules we know. Let's do the difference thing and the other one. So a sub n plus 1 minus a sub n. Let's take a look at that. We're looking at n plus 1 over n minus 1 plus 1 factorial. That's my a sub n minus a sub n is just n over n minus 1 factorial. So if I clean this up, this is n plus 1 over n factorial minus n over n minus 1 factorial. And if I want a common denominator, this one is only missing an n. I multiply this on top and bottom by n. I'm going to get n plus 1 minus n squared over n factorial. And looking at a few n's here, like for n equals 1, this top part, well, the bottom is always positive. N factorial is always greater than 0. Top here, we're trying to remember, and right, I'm checking greater than 0. We're trying to see, is this greater than or equal to 0 or less than or equal to 0? So that's all we're checking here. And if the bottom is always positive, it's not going to factor into my calculations. Let's just focus on the top. So when n equals 1, I've got 1 plus 1 minus 1 is 1, which is positive. N equals 2. I've got 2 plus 1 minus 4 is negative 1. That's negative. If I do n equals 3, I've got 3 plus 1 minus 9 is negative 5. That's negative. N equals 4. 4 plus 1 minus 16 is negative 11. That's negative. Looks like it started positive, but after n was greater than or equal to 2, this became a sub n plus 1 minus a sub n was less than or equal to 0. So this is looking like a decreasing sequence in the long run. And that supports what I had up here, right? It increased from n equals 1 to n equals 2, but after n equals 2, it started going down. If we look at the ratio test, we've got a sub n plus 1 over a sub n. This is, and I'm going to use these two versions right here. I have n plus 1 over n factorial divided by n over n minus 1 factorial. So I'm going to multiply by the reciprocal of the bottom to get rid of this complex fraction. So the bottom goes to 1, and I get n plus 1 times n minus 1 factorial. And then I have this n right here. And I'm going to write this, expand the n factorial as n times n minus 1 factorial. So this looks like this collapses down to n plus 1 over n squared. So that's my a sub n plus 1 over a sub n. And we'll check our monotone sequences again. What's going on here? If n equals 1, this is 2 over 1, which is 2. If n equals 2, this is 3 over 4. And on the ratio test, remember we're checking to see, is it greater than 1 or less than 1? So that was greater than 1. This is less than 1. N equals 3 is 3 plus 1 is 4 on top. 3 squared is 9 on bottom. This is less than 1. I'll do one more. 5 on top, and 4 squared is 16. That's less than 1. So eventually it shows that it's also decreasing here. Eventually decreasing also. And that's important to note that the first few terms of n don't matter. The first terms, and I'm going to say k terms, don't matter. That looks weird. There's not enough gap there. The first k terms don't matter as long as it follows a pattern after k. An increasing or decreasing pattern after k. Here, k was 2. Butt's getting sore. But it could go up to like 1,000. We could go up to 1,000 terms. We could go up to 10,000 terms. It doesn't, as long as eventually it starts going the other way, it has a limit. Okay. We do have another method that we can use. So let's talk about that. It's called the derivative method. It does require us to be able to take a derivative. Must be differentiable. So we're going to take a look. We're starting with f of n is a sub n. So f is a sequence, not a full function. But we take a look at f of x, rewrite as f of x. And then if f prime of x is greater than or equal to 0 for all x, I have greater than 1 here, but I don't think that's important. Then a sub n is increasing. That's the for all symbol. And change colors so you can see a difference. If the derivative is less than 0 for all x greater than or equal to 1, then a sub n is decreasing. I'm going to change that. I'm going to say 1. I'm going to say some value k. There's got to be a point where it cuts off and starts going the other way. Same principle that we had up here. But k should be greater than 1. So let's take a look at an example. And I'm going to use another page because this might take some room. Let's go with n minus the natural log of n over square root of n. That's our sequence. And we want to show that it's increasing. So we'll start off saying that we're going to let f of x equal x minus the natural log of x over the square root of x for x greater than or equal to 1. All right, so now we'll do f prime of x. We've got high prime, which is 1 minus 1 over x times low minus high times low prime. X to the 1/2 would be 1/2 x to the negative 1/2. All over low squared is x. Let me make sure I'm writing it in a way that you all remember. So let's see, how do I want to do this? If I multiply the top and bottom by square root of x, and I can do that because x is greater than or equal to 1, then this turns into, I've got 1 minus 1 over x. Square root of x times square root of x is x. It has to distribute to everything that's got a plus or minus between them. This is all one product. This is all one product. It's got to hit both. And actually here, I'm going to have it hit there instead. It'll cancel out the x to the negative 1/2. And we'll have minus 1/2 x minus ln of x. And on bottom, this was x squared times another square root of x. We get x to the 3/2 down here. Or x root x, whichever one you like. And now we can clean up the top a little bit. Distribute the x. I've got x minus 1 minus 1/2 x plus 1/2 natural log of x all over x to the 3/2. So, you know what? I don't like these with these 1/2. I'm going to multiply by 2 over 2. I get 2x minus 2 minus x. That's going to just give me x minus 2 plus ln of x. And on bottom, I have 2x to the 3/2. So let's rewrite that here where it's all nice and together. And let's start taking a look at some examples. If x equals 1, f prime is 1 minus 2 plus natural log of 1 over 1. Natural log of 1 is 0. 1 minus 2 is negative 1. This is just negative 1. So f prime of 1 starts off, or x prime, f prime of x starts off negative. What happens is we get larger. F prime of 2 is 2 minus 2 plus natural log of 2 over 2. Not over 2, but 2 to the 3/2. And we're looking for, remember, greater than 0 or less than 0. Increasing would be greater than 0. Decreasing would be less. So here it's less than 0. That's 0. Natural log of 2 is positive. The bottom is positive. I don't need to get an exact value. It's positive. If I do f prime of 3, I've got 3 minus 2 is 1. 1 plus natural log of 3 over 2 times 3 to the 3/2. Those are both positive terms, so that's greater than 0. And we can see that for x greater than 2, or effectively n greater than or equal to 2, f prime of x is greater than 0. So f of x is increasing. Therefore, that's the therefore symbol. Therefore, f of x is increasing, and thus f of n is increasing. Big takeaways. Do not just rely on the first term. And the first terms of the sequence, first k terms, first k greater than 1 terms of the sequence don't matter. Let's see, do I want to do another? No, I got the rest we're going to do when we start doing the other types of tests. That's good for this. That shows monotonic sequences. That's it for now. Peace.